It is my pleasure to introduce our next speaker, Doreen Dutke, from the University of Central Florida. The title of his talk is Fugler's Conjecture and Unitary Groups of Translations.
Thank you very much for the introduction, for the invitation in this very nice conference and context. This is work with Professor Jorgensen and some of my students, Piali Chakraborty, Brian Ducasse, and Corby Fernandez. But I guess most of the talk will be on the origins of Fuglede's conjecture, some things we think we should pay more attention to, and then some results that we got. So Fuglede's conjecture started with a question that Fuglede was asked by Siegel. So the question goes like this: if you take an open set omega in Rd and you look at the partial differential operators, you have to put an I here to make it symmetric. The 2 pi is just to make the spectrum a bit nicer. And you take a nicest domain possible, so smooth functions with compact support in omega. So these will be unbounded symmetric operators. That's just integration by parts. And the question of Siegel was, when do these operators admit commuting self-adjoint extensions? So you can always do self-adjoint extension for each, but the issue is for them to commute. An unbounded operator is self-adjoint if it's symmetric, the usual thing, and the domain of the operator should coincide with the domain of the adjoint. And the commuting part here means that all the spectral projections for all the operators commute. Yeah? So if it's self-adjoint, you can do spectral measures, spectral decomposition, you get the projections for each dj, and then we want all of these to commute. That's what we mean by commuting. And it's always an issue with these unbounded operators because the domain is not everything. And then in his wonderful paper from 74, Fuglede gave an answer to this question, which goes like this. You take omega in Rd, finite measure, open, connected, also important. Nicodeme, that's not as important. That means nice, let's say the boundary is smooth. Then there exist commuting self-adjoint extensions for the differential operator, if and only if omega is spectral. So for this talk, spectral means that there exists a subset lambda, we could think of them as frequencies, such that the corresponding exponentials E lambda form an orthogonal basis for L2 of omega. Yeah, so the existence of self-adjoint extensions and this with these little restrictions is equivalent to the existence of orthogonal Fourier series. For example, you take the interval, of course, that's a spectral with the spectrum lambda z. You take a square or a cube, it's spectral with spectrum z squared and so on. But this is a strange condition to check. It's sometimes hard, and even the simple domains like the disk or the triangle. And in this paper, Fuglede proved that they are not spectral. So you cannot do these commuting self-adjoint extensions. You don't have these orthogonal Fourier bases. And he proposed his famous conjecture in the same paper, saying that omega is a spectral set if and only if it tells by translations. And it took a while, and Tao found a counterexample in one direction for dimension bigger than 5. The counterexample was the union of cubes. And his counterexample was improved later by various mathematicians, Farkas, Matoshi, Koluntzakis, and others, showing that the conjecture is false in both directions for dimensions bigger than 3. A fairly recent paper by Lev and Matoshi, also a very strong, powerful paper in ACTA, proved that the conjecture is true for convex domains. And as far as I know, the conjecture is open in both directions in dimensions 1 and 2. And so Fugler had some restrictions in the, when he wrote the equivalence between the existence of self-adjoint extensions and this existence of Fourier basis of spectral, omega being spectral. And Steve Pedersen later found some improvements. He removed the nicotine. That was not a big deal, but even better, he removed the boundedness condition. So he redefined what spectral means, even for unbounded sets. So you have, first of all, f hat is the usual Fourier transform. You take a omega measurable subset, could be unbounded, and you replace the frequencies for the orthonormal basis, you replace that by a measure. So take mu to be a regular positive Borel measure, and we say that omega and mu form a spectral pair if when you do the Fourier transform on omega, so take functions on omega, you do the Fourier transform, you get a function which is in L2 of mu. And the map between, I guess, initially between a subspace this of L2 of omega and L2 of mu is an isometry. And so this map with dense range. So this map then extends by continuity to an isometric isomorphism between L2 of omega and L2 of mu. So I want the Fourier transform pretty much to be an isometric isomorphism unitary between L2 of omega and L2 of this measure. So the set omega is spectral if there is such a measure, yeah? In the case when omega is a finite measure, like in previous for Fugler, the two definitions coincide. And actually what you get is that mu will have to be a counting measure on a discrete set, and then you get your orthogonal Fourier series. All right, and so Pedersen removed the boundedness condition and the Nicodim condition, but of course you need connectedness. So if you take omega to be open and connected, then the existence of self-adjoint extension of the partial differential operators is equivalent to omega being a spectral set in this new sense. Yeah, so it's better than Fugler-Dess theorem. And we thought, okay, what happens if we have a disconnected subset? I will skip some technical details. The idea is, well, you have now a bunch of components, gamma I, for your set omega. To make things simpler, we assume that there are just finitely many components, and you still do the Fourier transform on each, but on different components, you'll have to adjust by various constants, and the constants could change with the point in I guess, the support of the pair measure. But in the end, it's kind of the similar thing. It's just if you change the component, you have to include this matrix. Like at each point, you have like a constant matrix. For example, if you have finite measure, so then the existence of commuting self-adjoint extensions is equivalent to the existence of an orthogonal basis, where on each component the function is E lambda, but with maybe different constants. Yeah, so it's like you have E lambda, but on different components you put different constants, and you want to get an orthonormal basis. All right, for intervals, we can actually describe all the self-adjoint extension. You have just one of course, for just one differential operator. There's no issue with the commuting part, but you have many self-adjoint extensions for a union of intervals, and those are uniquely determined by some boundary conditions. The boundary conditions are given by a unitary matrix B, and the domain will be functions which are absolutely continuous, the derivative in L2. And when you apply this unitary matrix to the vector of values of f at the left-hand points, you get the values at the right-hand points. And you have one-to-one correspondence, and the spectrum, so the spectrum will be given by the values lambda, for which you can make such a function where you put E lambda, different constants on different intervals, and you want the boundary conditions to be satisfied for this. So we know all the self-adjoint extensions of the differential operator. So there's no issue with spectrality here, yeah? It's just we are describing all the self-adjoint extensions. Of course, if you want omega to be spectral, then this B has to be special, yeah? All right, so then self-adjoint operators are in correspondence with unitary groups of operators. So if you take a self-adjoint operator on some Hilbert space, E, let's say it's a spectral measure, then you do, functional calculus, you can define a group of unitary operators. U of t is exponential 2 pi I t times a. And then U of t is a strongly continuous unitary group, meaning U of t is a unitary operator. You have the group structure, so it's like a representation of Rd. And it's strongly continuous. Okay, the converse is the famous theorem of Stone. So for just one, if U is a strongly continuous one-parameter unitary group on R, then there exists a self-adjoint A such that U of t is given by the same. That's the infinitesimal generator. And it works also for several dimensions. You just have to put 0 on each component except at the jth one where you put t, and the correspondence from before is here. So if you have self-adjoint commuting operators, then you have these unitary groups and vice versa, yeah, by Stone's theorem. All right, so now the question is, okay, so we have these self-adjoint extensions of the partial differential operators. We can make the unitary group. What's the extra property of the unitary group? And what happens is that what Pedersen called the integrability property, which means that if you translate just a little bit statement inside the component, then you really access translations. This is his definition, Pedersen's definition. So if you have, what it is for an arbitrary unitary group, we say that you has the integrability property if it satisfies the following condition. Whenever you take x in omega and you take a neighborhood and you move it a little bit, so that you stay in omega with the whole movement, yeah? We have that you really access the regular classical translation. Yeah, so that's called the integrability property. And the theorem by Jorgensen and Pedersen says that if you take any open set, doesn't have to be connected or anything, the following statements are equivalent. There exist self-adjoint extensions of the partial differential operators if and only if omega has the integrability property. Yeah, so locally, just inside the components, this U acts really as translations, as usual translations like that. And of course, the correspondence is the usual one given by the generalized Stone theorem. So again, in this case, we don't talk. It's not it's not the case for spectral sets. Just unless if it's connected. So if it's connected, then by Pedersen's theorem, the existence of extensions is equivalent to omega being spectral. And from the previous theorem, all the time, the existence of extensions is equivalent to this integrability property. So UT has to act as a local translation, as a translation just for small movement inside the component. So that's one thing. For connected sets, of course, for R, connected is just an interval, so that's not interesting. But in higher dimensions, omega spectral is equivalent to the existence of a group like this, which acts inside, if it's connected, it's just one component, acts as as a translation. Now what happens for disconnected? Then we have a stronger condition, which we called, initially we call it group of local translations. I will leave it as it is. So here we're asking, so we say that UT is a group of local translations if for any open subset V of omega and any T with the property that V plus T is again a subset of omega. So even if you jump components, yeah, from one component to another, U should still act as a regular translation. Yeah, so it's stronger than the integrability property. That's when you act as a translation just for small movement inside the component. All right, and we prove this theorem. So omega, well, here omega can be disconnected, anything, just open. Omega is spectral if and only if there exists a unitary group of local translations. So that means even if you jump components, you should still act just as a translation. And in terms of the existence of commuting self-adjoint extensions, you want that to happen, but you have to put the extra restriction that these weights, so this matrix, the matrix that appears in the characterization of extensions should have equal columns. In particular, if omega is bounded, that pretty much means that the weights are the same, so you just have a simple exponential, yeah? For different components, there's the same weight, so it's just E lambda. There's nothing, no different constants. All right. Okay, so but this is what I want to emphasize, that omega is spectral if and only if you can build such a group of local translations. Yeah, meaning the group property, it's unitary, so strongly continuous, and whenever it can act as a translation, even if you jump components, it should act as a just regular translation. All right, so now for unions of intervals, because we have the description of self-adjoint extensions, we can figure out what the associated unitary group is. So as expected, you'll have inside the component, inside each interval, you will have to act as a regular translation. And the problem is what happens if you take a point in one component and then when you add t, you go past, you go outside. So what will happen here, we'll have like a recurrence relation. The idea is first, okay, this beta I minus x means you take your point x and you move it so that it reaches the boundary, beta I, yeah? And at the boundary, what happens is, the way I think of it, the point splits into n points, one in each interval, with some probability. The probabilities are given by the values of the matrix, absolute value square. So you have this formula. And so we were able we can actually write a formula for U. And so let me give you a little bit of intuition. Yeah, I still have time. Let me give you a little bit of intuition of what's going on. So you take a point in your union of intervals, let's say it's in the ith interval. And let's say t is bigger than 0. So you want to compute uf of x plus t. So the way I think of it is you take x and you move it to the right. So initially you move it, you stay inside the interval alpha I, beta I. Nothing happens, it's just regular translation. Then once it reaches the endpoint, it will split into endpoints in each interval with some probabilities which are given by the absolute value square of the numbers in the matrix, in the boundary matrix B. So we have to talk about admissible paths. So we have to keep track of what's going on. Okay, first I1 will be just where you start, in which interval you start. Then if t is less than beta I minus x, so that means you stay inside this interval. That's it. That's your m equals 1. So that's the path. If t is bigger, then you have to go outside somehow the interval. So then you take this piece, which moves you to the endpoint, and then you'll go through intervals, the interval I2, I3, and so on, until you exhaust the value of t. So you keep adding length of intervals. Yeah, once you get to an interval, inside the interval is just translation, so nothing interesting happens. And until you exhaust this, so you'll have to IM will be like the where it ends, where the point x, I guess, plus t will end. These Li2, Li3, those are the lengths of the intervals. So you write t as the initial piece to get out of the interval, a bunch of lengths of intervals, and then you'll have some remaining part where how much you travel in the last interval. That's this r. We call it the remainder. M is the length of this admissible path, so the path is just keeping track of the indices. And each time you jump from one interval to another, you have to use a B. So you do a product. Yeah, you can also think in terms of random walks, but these are the absolute value square of these will be probabilities. And the end of the path is where you end. So you're in the IM interval, you go a little bit, alpha IM. So from the left point to you add the remainder. P will be the set of all admissible paths, ends will be the set of all ends of admissible paths. All right, so then the formula goes like this. You have your boundary matrix, your function in the domain. So if you don't have to jump from the interval I, where you start, it's just a translation. If you have to jump, then you look at all the admissible paths, and you'll have f at the end of this path, and you multiply by this b omega, yeah, which absolute value square, you can think of a probability. Each time you go through a boundary point, you multiply it by a b. All right, so that's here a little bit of technicalities. F was supposed to be in dB, so you have the boundary conditions. If it's arbitrary, then this will be almost everywhere. All right, so then we get this nice theorem. If omega is spectral, then what happens is u of f of x plus t will be, yeah, sorry, you'll have the local translation property. Yeah, this one. So even if you jump components, if x is in, let's say, the ith interval and x plus t is in the jth interval, still this formula works. Yeah. So that's one thing because it's spectral. The other thing is we have a formula which works no matter if it's spectral or not. So this formula works. So then putting this together, we were able to get a little bit of results. The first one is actually appeared at the same time Professor Koluntzakis let me know in a paper by Koluntzakis, Lev, and Matorshi. So if omega is spectral, then the gaps between intervals will have to be sums of length of the intervals of omega. And this actually is a consequence of the next one. So if you have x in alpha I beta I and x plus t is also in some other interval, then if you do the sum over all these b omega, so those are the products of the b's, when you keep the end of, you just look at the admissible paths such that the end is x plus t. This sum has to be 1. Actually, from this you get this almost immediately. And if you're looking at all the other ends of admissible paths, then the sum of the b omegas will have to be 0. And yeah, so like I said, a bit of consequences of this analysis. I just wrote maybe the easiest one, the nicest ones. If you have a finite union of intervals and that's spectral, then the gaps will have to be sums of lengths of intervals. Another thing that you can do with this kind of techniques is if you have a union of intervals and one of them is unbounded, and you want this unbounded set to be spectral, then it's almost impossible. It means it's all pretty much the union has to be R. Maybe you remove a few points. All right, that's it. Thank you very much.
Yes. Thank you. Is there any question to the speaker? If not, let us thank the speaker again.
Thank you.
Our next talk will start in 1 minute.